Good morning, class. Welcome to the first lesson on TOS. And the first lesson, if you remember, if I cast our mind back to what I said in that first little introduction there, right at the top was a static determinacy of frames. And this is it. Okay, so this note is just a 2-pager. There's it over there. If I do all of that, okay, it's a 2-pager. I've already uploaded it to Blackboard, and it's called static determinacy. I'll make it a bit bigger again so we can see it nicely. Right, I'm basically just gonna read through some of the bits, explain some bits, and explain some bits as I go along. Statically determinate plane frameworks rule. A framework which contains exactly the correct number of bars, bars or members, okay? If there's a frame there or a little truss made of 3 members, we call that members, okay? So that's 1, 2, 3. The text, the author calls it bars, okay? Required to keep it stable and statically determinate may be termed a perfect frame. Now, let's look at this frame over here, a triangular frame, okay? If I apply a force acting, you can see if I apply a force horizontally to the right at that point there, okay, that member there will be in tension because it's being stretched, and that member there will be in compression because it's being squeezed, okay? So if I apply a force horizontally to the right, or I apply a force horizontally to the left, that frame, and I'm assuming it's being fixed here, it's being fixed at the bottom 2 points there. By the way, these little circles are all pin joints, okay? That means the members are free to rotate about those points, but they can't move vertically or horizontally, okay? So if I apply force horizontally to the right or horizontally to the left, this frame ain't going anywhere. So in actual fact, a triangle is the perfect frame, okay? And if you look at if you go into a big steel structure and you look at the frames that make up the trusses, they're all made up of a number of triangles put together. Okay, so the next time you go into a big warehouse or big factory or steel building where there's roof trusses, check it out. You'll see they're all made up of a series of triangles because a triangle is the perfect structure. Okay, so if I look at this little frame here, I've got 1, 2, 3 members, and M will come to the formula. There's the formula we want to get to. Okay, M is equal to 2J minus 3, where M stands for member and J is the number of joints. So if I look at this frame here, I've got 1, 2, 3 members. Okay, so that's 3. If I add another member that way and that way, I've got 1, 2, 3, 4, 5 members. So here I've got 3 members and 3 joints. Here I've got 5 members and 1, 2, 3, 4 joints. Okay, and if I add another 2 on there, I've got 1, 2, 3, 4, 5, 6, 7 members, and I've got 1, 2, 3, 4, 5 joints, and so on and so on. Okay, so what we want to do, we want to determine whether a frame is statically determinate or not. Okay, if a frame is statically determinate, that means, now if you cast your mind back, as I said earlier, when we did the method of joints for solving a frame, okay, we took moments to find the reactions, then we summed vertical forces to find a second reaction, and then we summed horizontal forces to find the last reaction. Okay, so any frame that fulfills, that we can use those 3 equations for to determine the reactions, we say is a statically determinate frame. Okay, and to check whether a frame is statically determinate or not, that's the formula we use over there. M is equal to 2J minus 3, where M is the number of members and J is the number of joints. Okay, so, and if we test a frame and it's statically determinate, that means we, as applied mechanics students and as TOS students, we can go ahead and apply in some moments, some verticals and some horizontals, and solve that frame, okay, or analyze the frame using the method of joints or any other method. Okay, if M is not equal to 2j minus 3, that means the frame is not statically determined, or we say it is statically indeterminate, and then we at our level will not be able to determine it. Okay, so what we're going to do is we're going to do a check using the formula to check whether a frame is statically determinate. Then if it is, we can go ahead and solve it. Okay, so if you go across the page there's some examples there. I'm going to do this one over here in detail so we can see whether it's statically determined or not. Okay, and if I just go down there, if okay, I think I'll just work through it. Right, there's our first frame. Okay, frame number A. So the formula, let me get the formula quickly. The formula from the note is M is equal to 2j minus 3. So I'll state it over here. So M sorry about that. So M is my formula. Okay, so number of members, I'm going to count that. So M is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11. And the number of joints is 1, 2, 3, 4, 5, 6, 7. So J is equal to 7. Right, so let's see. So if I put 7 to there, so 2 times 7 is 14. 14 minus 3 is equal to 11. So therefore, M is in fact equal to 2j minus 3. So because the left-hand side here is equal to the right-hand side there, we say there that frame is a perfect frame. Okay, when M is in fact equal to 2j minus 3, we say it's a perfect frame. Okay, and a perfect frame means that there's no extra members. Okay, and any extra members, I'll make a note here, extra member structures, we say it is a redundant member. Okay, an extra member means we call it a redundant member in structures. It means if a member is redundant, it's too much, it's not doing anything, we can actually take it out of the structure and the structure will still remain stable. Okay, so when we solve this frame here, and if we find M is greater than 2j minus 3, then that frame will be an imperfect frame. Okay, that means the frame has extra members or redundant member. Okay, when we do the check and we find that M is less than 2j minus 3, we find that the frame is potentially unstable. Okay, so when M is equal to 2j minus 3, we have a perfect frame. When M is greater than 2j minus 3, we have a frame with potentially redundant members in the frame. And when M is less than 2j minus 3, we have potentially an unstable frame. Okay, so I'm going to go back to the answer there in the question. There's it over there. M is equal to 11, and 2j minus 3 is 2 times 7, because j is 7. So 11 is equal to 11. So therefore, we deduce that this frame is a perfect frame. Okay, right. Now, the next one there, you can do that yourself. I'm just going to point out a few things. So M, to count the number of members, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's why M is 17. The number of joints is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So J is 10. So therefore 2 times 10 is 20 minus 3 is 17. So therefore the left hand side is equal to the right hand side. So therefore this frame is a perfect frame. Okay, you can do that by yourself. Right, I'm going to take the next one. I'm going to take the next one here. Right, people, there I put in the next frame there. So the number of members, M. Oh, sorry about that. Sorry about that. M. So 1, 2, 3, 4, 5, 6, 7, 8. And J is equal to 1, 2, 3, 4, 5, 6. Okay. So M is equal to 8 and 2J minus 3. 2 times 6 is 12 minus 3 is 9. So M is equal to 8 and 2J minus 3 is equal to 9. So M is less than 2J minus 3. Okay, because that's equal to 8 and that is equal to 9. Okay, so, and if you look at the note there, if a frame contains more members or redundant members, we say it's hyperstatic. And if a frame contains less members than required, we say it is substatic. Okay, so let's check again. Number of members is 8. And by the way, people, I think I could have mentioned this last in applied mechanics. Even though that member there, we got one member there, one member there, we got one member there, one member there, one member there. Okay. Structurally, if we go to a steel workshop, okay, or timber workshop, that will be made as a single member, and that will be made as one single member. It's called the tie beam. But when we analyze it structurally, whether we do it manually or by a computer program called Procon, that's considered to be 3 members, and that's considered to be 2 members, even though it's 1 member in real life when it's made in the factory. Okay, right, back to this over here. So M is equal to 8 and 2 times 6 is 12 minus 3 is 9. So we can see from this frame here, this side is not equal to that side, so therefore M is less than 2J minus 3. So therefore we deduce that this frame is substatic. So with frame the same is substatic. And what does it mean? It means that we've got actually 1 or members too few to make the truss structurally sound. It could fail. Okay. Now we said there we want a perfect frame. So what can we do? Just this is not part of the exercise. This exercise is just to check whether a frame is statically determined or not. This frame here will be statically determinate. Okay, this frame will not be statically determinate because it's substatic. Okay, but watch this. We want to make this frame perfect. What can we do? Just watch this. I'm going to put in another member like so. So if I put in something like so, okay, right, let's do the test now. M is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So M is 9. Okay. The number of joints still stays 1, 2, 3, 4, 5, 6. So still 6. Okay. So M is equal to 9 and 2 times 6 is 12. Yippee! It's now also equal to 9. So in fact, M is equal to 2J minus 3. So if we put another member there, this frame will then become a perfect frame. Okay, but the test is to test whether the frame is perfect, substatic, or hyperstatic if it contains too many members. Okay, so people, so that is how we use this equation here to determine whether a frame is perfect, substatic, that means it contains too few members, or hyperstatic if it contains redundant members. Okay, I'll do one or two more in the next video.